Okay, in this video you're going to learn to make math models from data that you've taken in class. When you finish this video, you should be able to, number one, recall the math skills you've learned in math class about lines. Two, be able to create an equation from your data and graph by hand or by using a TI calculator. Three, know why you would want to make an equation from data. And four, deal with linear sets, data sets that are not linear. Let's start recalling the equation of a line from math class. So here is some data, quite a bit more data than we would ever take in class, and here's a best fit line through that. You'll recall from math class, an equation of a line has the general form y equals mx plus b, where m is the slope of this line and b is the place where the line intercepts the y-axis. And so in this equation, this line has a slope of 3.5 and a y-intercept of 0.25. In many data sets in science class, the y-intercept will be 0, but in general, there could be a y-intercept. Let's take a look at some data from an experiment. Pretend we're doing an experiment where we're trying to figure out where a frog is at every second. So we look at 1 second, 2 seconds, 3 seconds, 4 seconds, 5 seconds, and see that the frog is at these different distances. Perhaps these are in centimeters. And so we can go ahead and plot this data on our graph. All right, so here's the data plotted on the graph. Now, why would we want to get an equation from this graph? Well, one reason is to make predictions. There's a simple way to make a prediction from the graph, and that's to do something like this. Let's say we want to know where the frog is at 2.5 seconds. All right, well, we can read up from 2.5, and we can read over, and we can find that the frog is at position of 10 centimeters. So where is frog at 2.5 seconds? And we can make the prediction that it should be at 10 centimeters. And that's fine. But what if we wanted to know where the frog is at 10 seconds? Well, that's beyond the edge of our graph. Furthermore, we have to read up and read over, and that can be a little bit sloppy. So some reasons to actually do this process of making an equation is, one, it can be more accurate than simply reading off the graph, and two, can go beyond the graph. And those are two good reasons why you would want to make an equation from a graph. So let's go ahead and do this process of making an equation from a graph. All right, well, you've all taken math class before, so you have some ideas about doing this, I would guess. We want it to be of the form y equals mx plus b. All right, so in science class, we're going to prefer to use specialized symbols. Let me get those minimized over here, give us a little more room to work. We want to use specialized symbols, not generic symbols like this. This is the location of the frog, so let's call that L. And this is the time that the frog has been jumping. So we'll use specific variables for these quantities that make sense. Now let's go ahead and put in some other values. Like, for example, I think you can see right away that the y-intercept is 0. So we're just going to leave the b off because b equals 0. The y-intercept equals 0. Now let's go ahead and find the slope. Okay, so to find the slope, we can do something like this. We can choose 2 points on the graph, like we could choose 1.1, maybe 1.25, and that's a location of 5 centimeters. And we can go to 2.5, which we saw before was a location of 10 centimeters. Now that's going to help us find the slope because most of you know slope equals rise over run. And then in this case, the rise is going from 5 to 10. Rise overrun is going from 5 to 10. That's a rise of 5. And the run is going from 1.1 to 2.5. That's a run of 1.4. And so the slope is simply going to be 5 divided by 1.4. And if you go ahead and do that, you get a slope of about 3.5. So we can rewrite our new math model, our equation, as 3.5t. And there is our mathematical model that describes how the time the frog has been jumping relates to the location of the frog. Now let's go ahead and use that mathematical model to make a prediction. Where will the frog be after? Where is frog at, let's say, 10 seconds? All right, so we can use our mathematical model. We can put in our value, 3.5 is our slope, multiply by the time that we want to know where the frog is, 10, and 3.5 times 10 is 35. So L equals 35, double check our units, centimeters. And there we made a prediction where the frog would be after 10 seconds. Now this whole process is somewhat easier if you use your TI graphing calculator like a TI-83 or 84. And if you are interested in seeing how to get your calculator to tell you the equation of the line, to give you your mathematical model, then pause this video and go back to the instruction page for this assignment, and you'll find 3 different links that will take you to how to make your calculator give you the equation. There is a PDF that you could read, a short video, and a longer video. And you can go ahead and do that right now if you'd like. I would strongly recommend it since this is a fairly time-consuming process. And then come back to this video. Well, welcome back if you were away watching how to make a math model with your calculator. We have here a situation where our data is not linear, and that's a distinct possibility in our science class. So what do we do if the data that we have is actually not linear? So how can we get an equation from it if it's not linear? Well, there are a number of ways, but we'll focus on just one of them today. So I wonder what kind of graph this is. Let's see, it seems to be kind of an upward swoop like this. And this kind of graph, as you know, or you can look up in your binders, is called an increasing growing rate. An increasing growing rate. It's clearly not linear, and so it's going to be hard to write a y equals mx plus b equation, except that there's a pretty neat process called linearization. Linearization. And we're going to use this process to get an equation, a line equation from this data. And the first thing that we want to do is actually to linearize this. And here's how we're going to do that. Let me shrink this up a little bit smaller. Right, so the first step is to realize that, or to know that this kind of swoop, this increasing shrinking rate as we call it, has a mathematical relationship of being a squared relationship. So the relationship here is really that this squared is related to that. And so there's a nifty way we can linearize this or make it look like a line. And I'm going to show you that here. Get rid of this thing. What we're going to do is I'm going to grab another data table here that I've prepared. And this shows not the days and the number of ants, in my experiment, but rather the days squared and the number of ants. So maybe this is an experiment about how does the number of ants change over long periods of time, over days. And what we're going to do, because we recognize this graph as a squared shaped graph, if you don't, that's why I'm telling you, then what we can do is we can square this quantity and put it into here, and square this quantity. And so we almost create a new data table. 3 squared is 9, 8 squared is 64, 9 squared is 81, 11 squared is 121, and 15 squared is 225. You can do those on your calculator if you like. And then we have a new data table where the data has been squared. And as you're going to see, that's going to make our graph linearized. Let me erase these lines here. Shrink this data table up, get it out of the way. All right, so now let's grab a graph and let's see what happens when we graph this. Here's a graph that I've prepared. Notice that in this graph, when I plot not the time or the days, but rather the time squared, which is really squared of days, then I get a nice linear fit. Let me just show you with a nice line here. I get a nice linear fit to my data. All right, and because of that's a nice linear fit, now we can create a line, an equation of that line. So let me take my data table here and minimize it, get that out of the way. Move this over here. So now we can create an equation of this line. Now again, I would encourage you to do that in your calculator. But if not on your calculator, you can certainly follow the process you saw earlier in the video. In fact, why don't you pause the video right now and give that a try. Give it a try to find the equation of this line. Let me expand the data set back up there for you if you'd like that. Okay. All right, well, if you gave that a try, and hopefully you did, you found that the general form of any line is y equals mx plus b. In this case, we probably want the number of ants, so that's a good symbol there. The slope is that, time for t for time, and b for the y-intercept, and then we put in our numbers. I found the slope to be about 4, and this is times squared, times squared, and the y-intercept is 0. So in general, our mathematical model is a equals 4t squared, or number of ants equals 4 times the amount of time squared. That will allow us to make a prediction beyond the 250 days that we have here, 250 days squared that we have on our graph. So for example, let's say we wanted to find the number of ants after maybe 70 days. Okay, so we can go up and put in 4 and put in 70 days, but that's got to be squared because again we're dealing with a square function. All right, and so you can go ahead and try that on your calculator. 70 times 70 is 70 squared times 4. And I get 19,000 ants. That's a lot of ants. 19,600 ants. Okay, so this is the process of making a mathematical model. And you can now go on to the next step of the assignment. Actually, before you do that, I want to elaborate that there are each one of our kind of relationships, here's a few of them here, have a mathematical counterpart. So here's an increasing shrinking rate. Here's a decreasing shrinking rate. And here's an increasing growing rate like we just saw. So this is a squared function. In order to linearize it, you're going to square whatever's on the x-axis and then replot. This is a square root function. in order to linearize any graph like this, you're going to take the square root of your independent variable and then make a new data table with the square root of that, replot it, and find the equation of what should be essentially a line. Though with actual data, it won't be exactly a line, but it'll be very close. And this one is 1 over x squared. And again, so for this kind, you would do 1 divided by the square root, or 1 divided by your independent variable squared, make a new data table with that value in it, and plot that and find the equation of that line. Okay, at this point then, you can go on to the next part of the assignment.